Okay, we're going to take a quick look at how does a least squares regression actually work. So this is like what you use to find the line of best fit. So the idea here is that I have some points, x1, y1, x2, y2, and I have these all the way out to xn, yn, and I want to find some line f of x is a sub 0 plus a1x, right? Where if I add up I equals 1 to n, the distance between the y values in the points and the functional values where they're supposed to land squared is minimized. So if I can minimize that, I have a least squares regression. Now we're going to kind of give a cartoony vision of how this kind of works. Using matrices, we're not going to go too deep into the theory here because the application is what is important, but we're going to give you an idea of why matrices kind of work here. Okay, so conceptually what we've got going on here is that each of the y1s should be equal to where the function lands, right, plus y1 minus where the function lands, right? Okay, so the y2 should be, this is just like adding something in and then subtracting it back out. That's all we're doing here, right? And this goes down to yn f of xn plus yn minus f of xn. So we just basically added the functional value in and then took it back out, right? So what we're going to do is we're going to let this like ei be this thing, yi minus f of xi. Right, so that's ugly. Let's fix that a little. yi minus f of xi. Okay, so what we're going to do is, this is our errors, right? These are the things that we're going to add up, square, and then try to minimize, right? So if I rewrite this, I get y1 is f of x1, 1, that should be a 1, plus e1, why do I keep writing i's? E1, y2 should be f of x2 plus e2, all the way down to yn is f of xn plus en, right? But I can kind of go a little further here, right? So let me clean this up a little bit further. Because each of these f of x's, oops, let's do that again. Each of these f of x's is earlier said is a lot going to be represented by this line, a0 plus a1 times x1, right? a0 plus a2 times x2 times a0, sorry, that should be a1, right? Plus a1 times x3, or xn is what I'm dealing with here. Sorry. All right, so this is, the function is actually the line plus some error, okay? So here's what we're going to do, is we're going to let, let's clear out some of the space in the top here. I don't have to start a new page. Okay, so we're going to let some matrices exist. We're going to let this Y matrix be just the column of Y's, Y1, Y2, down to Yn. We're going to let there be an A matrix, which is going to have two things in it, A0 and A1. We're going to have an X matrix, which is a little odd. It's going to have a column of 1s, and then it's going to have a column of the X's, X1, X2, down to Xn. And then we have an E matrix, right? And the E matrix is just this column of E's, E1, E2, down to En. All right, so let's think for a second here. If I do this, well, it's clear that the left side of my system of equations here is just the Y matrix. Now, if you think about what's going on here, if I multiply this A matrix times this X matrix, I get a X. And then this last column is just this E matrix, right? So let's make that just a capital E there. There we go. The E matrix. Okay, so what are we trying to do here? We're trying to find the A matrix that makes the squares of the E matrices minimum. Okay, so this means there's a pathway here. Now, in all honesty, the way we're going to write E squared here is E transpose E, and that will get me an idea of E squared in this type of system. And that's what we're trying to minimize. Now, lots of people have done a lot of work on this, and you can go up into Google and Google the actual proof for what this is, but we need the A value in terms of X and Y that's going to minimize E, and it happens to work out that that A value is X transpose X inverse times X transpose Y. So this is like the key value that will actually cause this minimization. Now again, I'm not going to do the deep dive into that for that here. Those of you who are interested, there's plenty of resources on this on the web, but this is just something I'm going to take as a given right now, because if I do the deep dive, I'm going to lose the important piece of this, is that you can use matrices to do this minimization. All right, so let's take an example. All right, so let's get 5 points. So let's say I have the point 1, 1, 1, 2, 2, 3, 4. We don't want them to be nice and linear, so we're going to make them not linear. 4, 4, and 5, 6, right? So according to what we said here, I can make an X matrix. Now, the first column of my X matrix is all 1s. 4, 5, and then I go 1, 2, 4, 3, 4, 5, right? Those are my X values. And then I make a corresponding Y matrix with the Y values. So that's 1, 2, 4, 4, 6. Okay. So the argument is that if I take A to be X transpose X inverse times X transpose Y, I will get the coefficients for the least squares regression. So let's actually do that. Okay, so I have my MATLAB command window, and I'm actually going to let MATLAB do the work here. So I need 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, right? So that's my X matrix. My Y matrix is just the column of my Y values. So that's going to be 1, 2, 4, 4, 6. Okay, so A should be X transpose times X, but I need to take the inverse of that, right? Plus or sorry, times, that's times X transpose times Y, right? And lo and behold, I get a nice little matrix here. So what does that mean? That means that I now have the constant, negative 0.2, and the slope, 1.2 for my equation. So let's write out that solution. Okay, so we got that A was negative 0.2, 1.2. So this means that the line y is negative 0.2 plus 1.2x is the linear regression line, or the line of best fit for those points. So Go matrices, yet another thing that we can do with them.